Welcome, everyone. I'm Jonathan Weiner. I am the co-director of the Duke Center on Risk, along with my colleague, Professor Mark Borsick, who's also here with us, and with Tyler Felgenhauer, a research scientist with us at the Duke Center on Risk. And we're very pleased to welcome you to this webinar today, one in our series on planetary risks. And today our topic is asteroids, planetary defense, and global catastrophic risk. We're delighted to be joined by two superb speakers on this topic, Dr. Seth Baum from the Global Catastrophic Risk Institute and Dr. Elizabeth Pate-Cornell from Stanford University. So I'll introduce our two speakers, and each of the speakers will speak for about 20 minutes, and then we will have question and answer. A couple of people have submitted questions in advance, and we also have a Q&A function on Zoom for you to submit additional questions. And Tyler and Tim, I want to thank you both for arranging for this webinar, and also ask you that if you see that there's a question that I'm missing, please bring that to my attention. And depending on our time, we may have the opportunity to invite attendees to unmute and pose their questions orally. We'll see how many questions we have and how much time we have remaining. If not, then I will try to read the questions that have been submitted in advance or in the Q&A. Okay, so let me introduce both of our speakers, and then I think Seth Baum will be the first, and then Elizabeth Pate-Cornell is going second, if I recall correctly. Dr. Seth Baum is the co-founder and executive director of the Global Catastrophic Risk Institute, which is a nonprofit, nonpartisan think tank that studies a range of catastrophic risk scenarios and response options. He's also an editor of the journal Science and Engineering Ethics and an affiliate of the Center for the Study of Existential Risk at Cambridge University, UK. Seth, we're really delighted to have you here with us today. And then our second speaker will be Dr. Elizabeth Pate-Cornell, who is a professor and the founding chair of the Department of Management Science and Engineering at Stanford University. She's a member of the National Academy of Engineering, the French Académie des Technologies, the Draper Lab Corporation, the NASA Advisory Council, and a distinguished visiting science at JPL, the Jet Propulsion Laboratory. And near and dear to our hearts is that she is a past president of the Society for Risk Analysis, SRA. And if anyone is interested in joining SRA, Society for Risk Analysis, I encourage you to do that at sra.org, and our annual meeting is coming up in about a month in December. And if you're interested in getting more information and being on our list for these webinars and other activities of the Duke Center on Risk, please email us. Tyler Felgenhauer at Duke would be the probably best contact person. So thank you both, Dr. Baum and Dr. Pate-Cornell. Really looking forward to this discussion of asteroids, planetary defense, and global catastrophic risk. So Seth Baum, please go ahead. We look forward to your talk. Oh, and also the file of Seth Baum's slides are available for viewing by attendees separately during the talk, and the link to that is in the chat. Thank you, Tyler. Go ahead, Seth.
Thank you. Yeah, thank you. Thank you for the very nice introduction, and it's an honor to have the chance to speak with you all today about asteroid risk, especially on a nice quiet day like today when there's not much else going on in the world. Yeah. So the title of my talk is on asteroids as a case study in global catastrophic risk, but it's actually more of a case study for risk in general. The theme we will explore is the idea that asteroids cut against conventional wisdom in both risk science and risk policy. In risk science, one might think that there is greater uncertainty about low frequency, high severity risks due to the scarcity of data. In risk policy, one might think that the same low frequency, high severity risks tend to get less policy attention for a variety of reasons, including that the events are too rare for citizens and policymakers to have prior experience with them. However, for asteroids, at least at first glance, the reverse holds. Low frequency, high severity asteroid risk is actually less uncertain and gets more policy attention than more moderate asteroid risk. I say at first glance because upon closer inspection, the situation is more complicated. I hope that by taking a closer look, we can learn something not just about asteroids, but about risk science and risk policy more generally. If we can go to slide 2, a small housekeeping note. I've put the slides online for anyone who wants them. That's in part here. I'll just type the link in one more time into the chat window. It's in part because my video is liable to cut out. I apologize in advance if it does, but we can keep up with the presentation regardless. Once you have the slides, it's fine with me if you share them with your colleagues. I do ask don't post them online yourself. You'll also see that the slides are numbered in the top right corner. I will refer to these numbers when changing slides. So slide 3 shows the spectrum of risks from high frequency, low severity to low frequency, high severity. Global catastrophic risks are the most extreme low frequency, high severity risks. In principle, risks at all points on the spectrum can be the same size in terms of frequency multiplied by severity, and this graph shows them to be the same. In practice, it is sometimes argued that global catastrophic risks tend to be the largest. The argument is sometimes made that the severity of the global catastrophes is just that large, and it's often based with reference to future consequences. A catastrophe resulting in human extinction would, of course, eliminate all future generations. Additionally, as slide 4 shows, a catastrophe resulting in the destruction of global human civilization could potentially also have severe long-term consequences, especially if the survivors are unable to maintain or recover some combination of agriculture and industry. The graph on slide 4 shows severity measured in terms of human welfare, though other metrics could be used. It is important that severity is measured in some sort of human terms. Likewise, the collapse of global human civilization is a good working definition of global catastrophe. Slide 5 shows what I at least think of as being conventional wisdom on risk science and policy. The asterisk at the top is there to mark that it's hard to say what really is conventional wisdom on risk. On risk science, we might think that low frequency risks tend to be more uncertain because they have less data available. The idea of black swans, for example, is relevant here. On risk policy, I'm using work from Jonathan Weiner that's showed on slide 6. The idea here is that people tend to underestimate high frequency risks because they're so mundane they fade into the background, like car crashes, for example. People also may underestimate very low frequency risks because we generally have no prior experience with them. For example, global human civilization has never previously collapsed. In the middle is a sweet spot where we have just enough experience with the risk that it catches our attention when an event happens, like plane crashes. This might not yet be conventional wisdom, but it does make a lot of sense to me. And I can say that among people who study global catastrophic risk, there is a general sense that policymakers tend to neglect global catastrophic risk in favor of more moderate risks. As slide 7 shows, asteroid risk appears to work in the opposite direction. Despite what one might expect, it can seem that low frequency, high severity asteroid risk is actually less uncertain and gets more policy attention than its more moderate counterpart. We can focus on the orange box and leave out the high frequency portion because there isn't really a significant high frequency asteroid risk. Objects from space do collide with Earth on a daily basis, but they are too small to harm humans. Slide 8 shows the basic idea for asteroid risk science. The high severity risk comes from large asteroids, which are easier for astronomers to detect. Likewise, a larger portion of large asteroids has been detected, making that part of the risk less uncertain. This figure is from 2014, but the basic picture has been like this for many years and remains like this today, albeit with more asteroids discovered. Slide 9 shows the basic idea for asteroid risk policy. Policymakers have long been interested in large asteroids, which is generally taken to correspond with the low-frequency, high-severity portion of the risk spectrum. It is only more recently that policymakers have expanded to cover more moderate asteroid risk. The data shown here for the United States, though I believe the same trend is found in other jurisdictions. Now, I said that this basic picture for both the science and policy gets more complicated when you take a closer look. We're now going to do just that. Slide 10 shows a more detailed risk diagram from a recent NASA report. The left vertical axis shows n, the estimated number of asteroids of various sizes. The right vertical axis shows the corresponding estimated impact interval. Along the top is impact energy in megatons, and along the bottom is asteroid diameter. The three down arrows are Chelyabinsk, a 2013 collision event in Siberia, Tunguska, a larger event in 1908 that was also in Siberia, and Chicxulub, the event that's believed to have killed the dinosaurs. Versions of this diagram are shown repeatedly in asteroid risk analyses. There is still some uncertainty in these numbers, but overall they seem to be pretty reliable. Slide 11 shows the human consequences of asteroid collisions taken from the same NASA report. It shows the largest risk for large asteroids of around 1 kilometer diameter. This figure and the underlying analysis is a good representative of the treatment of human consequences in asteroid risk analysis. As discussed earlier, it's important to measure severity in human terms. And here is where asteroid risk science gets more complicated. Slide 12 summarizes. First, the direct physical effects, including the explosion and the seismic shock or tsunami, are relatively well understood, and ongoing research improves our understanding. It's based on detailed studies of local and regional catastrophe effects, often drawing on other types of catastrophes such as nuclear explosions and tsunamis generated by other events. And we're on slide 12 right now. Second, indirect effects such as economic, political, and cultural effects have received a lot less attention and are likewise a lot harder to study. Here the uncertainty is very high. The same also applies to the global environmental effects, which come from the collision sending dust and other material into the stratosphere, where it spreads around the planet and blocks incoming sunlight. The asteroid risk literature has focused on thresholds above which there would be global catastrophe, but these thresholds have not been rigorously defined, and they have not taken into account important dynamics, such as how effectively human civilization would respond to this type of global environmental change. The diagram on the previous slide had a pretty good handling of direct physical effects, or the human consequences of direct physical effects, but no accounting of indirect effects and only a very crude accounting of global environmental effects based on best guess estimates with no apparent empirical basis. So that diagram is not nearly as reliable as the diagram on the slide before that, which is on the physical and astronomical dimensions of asteroid risk. To illustrate the considerable uncertainty in the human consequences, I will share some detail on inadvertent nuclear war. The idea here is that the explosion from an asteroid collision could be mistaken as a nuclear attack, prompting a state to respond by launching their own nuclear attack in what they believe is a retaliation, but is in fact the first strike. My group also studies nuclear war risk, and at first I was pretty skeptical of the idea of inadvertent nuclear war from an asteroid collision. I figured that the collisions were too infrequent and too readily distinguished for nuclear attacks. However, in studying this further, the risk now seems more significant. Slide 13 shows the 2013 Chelyabinsk collision event, which caused extensive damage on the ground. Chelyabinsk is just 130 kilometers away from Snezhinsk, a Russian nuclear facility comparable to Lawrence Livermore National Laboratory. Suffice to say, a 500 kiloton explosion at a major nuclear facility is a matter of national security concern, though not necessarily one that would result in inadvertent nuclear war. Slide 14 shows other events that may also classify as near misses for asteroid-induced inadvertent nuclear war. The asterisk at the word near at the top marks that these events may or might not have actually come close to resulting in nuclear war. Indeed, how likely such an event is to end in nuclear war is a crucial but highly uncertain parameter. Nonetheless, these incidents are enough that I think this risk could be significant. And these are just the incidents that I've been able to identify so far. Probably there are others that I've missed. To put this in perspective, slide 15 shows a nuclear war probability model that my group has developed. It maps out the various pathways to nuclear war. At the top in pink are intentional pathways in which a state decides to initiate nuclear war. At the bottom in blue are inadvertent pathways in which a state initiates nuclear war after believing the nuclear war has already started. All the way at the bottom are false alarm pathways in which something other than a nuclear explosion is mistaken for a nuclear attack. Slide 16 shows data on nuclear war incidents that we collected for each pathway. They're all near misses, or maybe not so near misses, except for World War II in the top left corner, which is the one actual nuclear war that has occurred. The bottom 4 lines show 15 false alarm incidents, including the 1995 Norwegian rocket incident and the 2018 Hawaii Emergency Management Agency alert incident. None of these incidents involve asteroids because the asteroid incidents are not well documented in the nuclear war literature, and because my group had not yet begun our general study of asteroids, so we hadn't learned about it from that. What strikes me about this is that for all 15 of the false alarm incidents shown here, none of them involve actual explosions, yet some of them were very nervous episodes. The Norwegian rocket incident, for example, something came quite close to resulting in nuclear war. An asteroid collision can involve an actual explosion of the same size as a nuclear detonation, which could make it even more likely to result in inadvertent nuclear war. Slide 17 translates nuclear explosions into asteroid risk. The yellow box at the top shows the energy range of current nuclear weapons from the 300-ton US B-61 to the 5-megaton Chinese DF-5. The 300-ton to 5-megaton range corresponds to asteroids of 1 meter to 50 meters, which collide with Earth every 0.6 to 3,000 years. The Chelyabinsk event in orange fits well within this range. What this diagram shows us is that inadvertent nuclear war creates the prospect of global catastrophe from a much smaller and more frequent class of asteroid. Slide 18 brings us back to the conventional wisdom for risk science. On slide 18. The astronomical side of asteroid risk does indeed go against the conventional wisdom, but the human consequences do not. There is significant uncertainty for all of the human consequences of asteroid collisions, but the most uncertainty is for the highest severity end of the spectrum. A more general lesson for risk science may be that extreme, low probability, high severity risks can have physical attributes that generate larger signals, making them easier to study. For example, perhaps a geological record may have better evidence of large volcano eruptions than smaller ones. I don't know for sure, I'm not a volcano expert, but perhaps that could be the case. There's similar things for other risks. This is all important information, though it's not enough to characterize the risk in human terms. The human consequences at the more severe end of the spectrum will, I think, tend to remain more uncertain. Now, on to risk policy. First, given all the uncertainty, it is fair to ask whether we even need to quantify these risks in the first place. Slide 19 shows one policy in which we do. Nuclear explosives may be an effective way to deflect Earthbound asteroids away from Earth, preventing a collision from occurring. This involves space missions to explode the nuclear device near an asteroid well before it approaches Earth. On the other hand, doing this could increase the risk of violent conflict on Earth due to how programs for nuclear deflection intersect with nuclear weapons issues. This is a risk-risk trade-off. I've attempted to assess how the trade-off is resolved in order to inform policy on the use of nuclear explosives for asteroid deflection. There's a lot that can be said about the trade-off, but it is very difficult to resolve in one direction or another. Slide 20 brings us back to our original policy observation, which is that policymakers have paid more attention to the low-frequency, high-severity risk from large asteroids. The prospect of inadvertent nuclear war from asteroids means that high severity can also come from small asteroids, though this doesn't appear to have factored into the policymaking. This leaves the question of why policymakers have focused on what from their perspective would be the low-frequency, high-severity portion of the risk spectrum. It would be great to see some studies interviewing asteroid policymakers on this. Meanwhile, we can at least advance a few hypotheses. Slide 21 revisits two diagrams from asteroid risk science. The top diagram derives from the fact that large asteroids are easier to detect. This could make large asteroids a more attractive policy target. It does make sense for policy to start with the asteroids that are easier to detect and gradually expand to the more difficult ones. Similarly, prior discoveries of large asteroids mean that there has been less uncertainty about them, at least in terms of the astronomy and not the human consequences. Given that, perhaps policymakers have given more attention to large asteroids because they favor addressing risks that they see as having less uncertainty. Looking at the bottom diagram, asteroid risk analyses have found the larger asteroids to be the larger risk in terms of human harm. This is from a 2017 report, but earlier studies have found the same trend. These analyses are flawed, especially in their characterization of the human consequences of indirect effects and global catastrophe, but they may have nonetheless motivated policymakers to focus on larger risks. Perhaps policymakers would shift their focus in consideration, in consideration of a more nuanced study of the human consequences, such as via accounting for the risk of inadvertent nuclear war. Finally, slide 22 suggests two more hypotheses. So the slide on slide 22 shows a direct quote from one of the first asteroid policy documents. The first line references the Chicxulub asteroid that is believed to have killed the dinosaurs. This is a famous asteroid event, famous enough that it could make a large asteroid collision more psychologically available in people's minds than would be expected, given that no one has ever lived through such an event. Additionally, Hollywood movies such as Deep Impact and Armageddon could play a similar role. Likewise, the more moderate asteroid risk is still for events that happen relatively infrequently, making these relatively easy to overlook. Finally, the line at the bottom articulates the idea of risk as frequency multiplied by severity. It acknowledges that high severity risks can be important even if the frequency is low. This is the same basic reasoning that motivates my colleagues and I to be concerned about extreme catastrophic risk. I, for one, find it very encouraging to see this reasoning used by policymakers. It suggests that policymakers can overcome whatever tendencies they may have to underestimate low-frequency, high-severity risks, at least in some instances. So perhaps asteroids are a counterexample to the conventional wisdom that policymakers tend to under-address the low-frequency, high-severity risks, at least to the extent that this is conventional wisdom in the first place. Or perhaps policymakers don't under-address the low-frequency, high-severity risks per se. Maybe they under-address risks that are more uncertain or less psychologically available, which are often but not always the low-frequency, high-severity risks. Or perhaps policymakers favor risks that appear to be larger to them in terms of frequency multiplied by severity, and risks that are easier for them to address. There may be some truth to all of these hypotheses. In other words, the stars may have just all been aligned in favor of policy on the risk from large asteroids. In that case, asteroid risk may just be an outlier. Or perhaps there are opportunities to better align the stars for other low-frequency, high-severity risks as well. Given how important these risks may be, opportunities to address them could be well worth pursuing. Thank you.
Thank you very much, Seth Baum, for a very intriguing presentation that starts with the risk of asteroids, but goes beyond that to include the risk of the accidental or misidentification of an asteroid as a nuclear attack, and the human consequences and the human psychology then of why we actually have paid some attention to asteroid risks, even though they may be low frequency, high consequence. Those are good questions we can take up in the Q&A period. So now let me welcome our second speaker, whom I've already introduced, and you can see the, for attendees, you can see the biographies of each speaker in the invitation email and flyer. Dr. Elizabeth Pate-Cornell at Stanford University, past president of SRA. We're so grateful to you for taking the time to be with us today and look forward to your talk. I think you may still be muted. I think you need to unmute your, on the Zoom image, it still shows that your microphone is on mute. Tim, are you able to help Dr. Pate Cornell unmute?
Yes, Doctor, if you look at the bottom of your screen, there should be a microphone that says mute. You need to click on it so that it is oh. Maybe Dr. Cornell, if you attempt to leave the meeting and rejoin real quick, that might be easier. It seems like you're having a microphone issue at the moment.
Jonathan, there was a question for Seth while we wait in the Q&A, if you can see that.
Okay, yes, I'd be happy to pose that question. Oh, okay, maybe Elizabeth Pate Cornell is now going to rejoin. So thanks, Tyler. Seth, there was a question for you about, on slide 19, you discussed potential weakening of nuclear taboos if preparations are made to use nuclear explosives for asteroid deflection. Do you know of any approaches to try to quantify the risk associated with taboo weakening?
It's a good question, and I looked at the matter briefly in a paper of mine on the risk-risk trade-off. I will post a link to the preprint for it in the chat window. The short answer is not really, which is to say it hasn't really been attempted. I did not dare attempting to quantify it with any precision just because of how difficult the matter is. This is one of the aspects of the risk that is not readily quantified. That said, it is also one that is hard for there to be clever policy that kind of works around it. Some of the other aspects of the risk, maybe with the right policy approach, you could avoid it. But with this, it seems like just an aspect of nuclear explosives programs, nuclear asteroid deflection programs that we maybe just have to live with.
And I hope that you can hear me by now. Can you?
Yes, yes.
I needed my local technician to help.
So we may return to that question again after Dr. Pate Cornell's talk, but now Dr. Elizabeth Pate Cornell, please go ahead. We're looking forward to your remarks.
Thank you. Seth, I want to say first how much I've appreciated your talk. Now I'm going to focus more on asteroids. And I want to say this was a project done by a group of students supported by JPL under the leadership of Jason Reinhardt. And then we have continued a little bit on this stuff. Next. Okay, so let me say the Stanford Engineering Risk Research Group has done a lot of quantitative models for major risks, seismic risk, medical problems, space systems, nuclear weapons arsenals, cyber threats, and what I'm going to talk about, which is asteroids. All that to say that I am not a specialist of asteroids in particular, but more generally risk. Next. So what we do is to try to inform decisions about planet defense measures, both in space and on the ground. Our analysis, as usual, is based on probability and systems analysis and loads and capacities, the loads of an asteroid hit and the capacity of what's on the ground to take it. So a lot of uncertainties everywhere. Our results are probability distributions generally, and all the inputs that you're going to see are the probabilities of asteroid characteristics from all the information we could get our hands on, and not only statistics, but also publications and expert opinions. So we have data from physical measurements of what has been observed, but also other knowledge. So there are asteroids we have seen, others we have not, but we know they are there. So the questions that we try to address: is the risk tolerable compared to others? Are there possible countermeasures? Are they effective? And what are the trade-offs, so that we can allocate our risk the best we can? Next. Okay, so just one joke: the dinosaurs may have had a point. After Chicxulub, about, 66 million years ago in Yucatan, they are two casually chatting dinosaurs are saying, all I'm saying is now is the time to develop a technology to deflect an asteroid. Back to your point, Seth. Next. This is a history, the map of the asteroid airburst events between 1994 and 2013. Our source is NASA, and what's important is to see how many there were, and of very different sizes. Next. The sizes. So we looked first at the asteroid belt between Mars and Jupiter, and there's a wide range of sizes, from Vesta, which is 530 kilometers, to less than 10 meters. Next. So an example of hits on Earth is the Barringer crater in Arizona, 1.2 kilometer in diameter, 170 meters deep. It was an asteroid impact about 50,000 years ago, and the asteroid diameter was probably about 50 meters. It was made of iron and nickel, which is only one type of asteroid. Next. The worst case that we know is Chicxulub in Yucatan, about 66 million years ago, a crater of about 7 miles diameter, and it caused what's called the Cretaceous tertiary extinction, with sudden mass extinction of 3/4 of the plant and animals species on Earth. So that came pretty close to finishing the whole story. Next. So we are looking at two kinds of events. The asteroid actually hits the Earth, that was the case in Chicxulub, and destroys most of what we know was life on Earth at the time. And these kinds of asteroids can have an impact by changing the climate, causing a global winter caused by ejecta and projecting huge amounts of sulfur in the atmosphere. Then there's the other case: the asteroid bursts when it hits the atmosphere and before it hits the ground. That was the case in Chelyabinsk. Next. I'm sorry, there is a construction next to us. The effects of the countermeasure on the ground, there are two kinds: the local effects, the effect of the impact, if the asteroid actually hits the ground, the explosion against the atmosphere, so a surge of pressure, and the countermeasures on the ground to protect the population if we have enough time in civil defense, evacuation and protection. Next. Countermeasures in space, that's, I think, an important part. Gravity pull, you put a mass next to the asteroid to deflect and shift the orbit. Kinetic hits, hit by a high-speed aircraft, but then you're limited in the size of the spacecraft and its mass. And nuclear explosion, which is what Seth mentioned, near an asteroid, so that you have irradiation of a large fraction of the surface with X-rays and neutrons of very high temperature, change in the velocity and trajectory of the asteroid. So in principle, there's a nuclear treaty that bans nuclear explosion in space, but it was essentially for defense cases. And there seems to be an understanding, including with the Russians, I believe, that in case it is to protect the Earth, that's an entirely different story. Next. So how do we look at the impact assessment? Now, the current detection of an asteroid is done by cameras and telescopes. And we don't have much time, generally less than 2 weeks. And for Chelyabinsk, it was just a few hours. But it could become years because we have two main systems of detection. One is NASA Sentry at JPL. The other one is the European Space Agency system. And the objective is to determine the size of the asteroid, the trajectory, probability of impact, and the time to potential encounter. So main problem, trajectory and timing. And what are the characteristics of the asteroid that matter? Its diameter, the size, the velocity, the density, and we're going to see several kinds of asteroids, the angle of entry in the atmosphere, and the density of the ground at the point of impact, which determines a lot of the effect. Next. So the risks posed by future asteroid impact, statistics do not provide sufficient information. Why? Because the human population changes. We have enormous uncertainties about the size, the angle, and the composition of the asteroids. And the question is, what are the chances that it hits a large city? And what also would be the global consequences for Earth and the effects on the climate and life? Next. So we did a risk analysis based on loads and capacities, as we do very often. So the load is the asteroid impact, the capacity is the vulnerability on the ground, and our objective is to assess the result on Earth. And what we did is to partition the Earth's surface into basic areas and assess the probability that each area is hit. And that area includes a large city, and that's a very small probability because most of the Earth is covered by oceans. Next. So the key relevant characteristics, the nature of the asteroid. Is it stony or is it metal? And metal, by the way, is a very small probability of 5%, 15%. The size, for example, Chicxulub was about 7 miles. We don't know really. Perhaps there was more than one. The density, Chelyabinsk, it was 3.3 metric tons per cubic meters. The angle at which it hits the atmosphere, and that was the worst case at Chicxulub was 60 degrees because it allowed the release of billions of sulfur thrust in the upper atmosphere that blocked the sun. So there are major uncertainties about O5 when looking ahead. Next. So the impact effect depends on the ground density, but also on the radius of the crater, the fireball, the ignition, the seismic effect, the blast, and the ejecta mass. And my students looked at originally the model by Collins et al. In 2005, and with additional uncertainties on the density, the angle, the velocity, and the diameter. Next. So this is the model structure. The key factors and the impact on the left, you see the input, the density, the angle, the velocity, and the size. And I put the source of our information from people who had done work on this before. The composition, the ground density, and we used the effect model of Collins to get the radius that I was talking about and the ejecta mass. Next. So the main sources of data, statistics and expert opinions at JPL, and again, Paul Chodas was extremely supportive and helpful, knows a lot about it. Publications, but also from Oak Ridge National Lab, we got the global population database and the division of the Earth that they have done and published. Next. So what was interesting, we looked at the 100-year probability of an impact with the global cataclysmic effect, and we found that asteroids of less than 1 kilometer diameter account for 75% of the probability of cataclysmic hit over 100 years. And yet, as you can see, we look both at the asteroid populations that exist and we know exist and what we have observed. Next. Okay, so loss simulation and the effect of civil defense. We used the grid of the Earth created by the Oak Ridge National Lab. The size of the grid elements is only an arc, 30 by 30 arc seconds, about 30 meters. And the circular dimension superposed to the population gave us mortality rate with different radius of effect and benefits of defense. So we looked at the effect of civil defense because for the moment, that's the best thing we can do. And essentially, we found that the good civil defense decreases the risk by a factor of 2, can decrease the risk of by a factor of 2. Again, given that we have enough time to do something. Text. Okay, so now let's talk back to space, the gravity attractor, the kinetic impactor, and nuclear explosion. And the key issue is the effectiveness and the lead time that it will take to do something in each of these things. For example, a gravity attractor will take a very long lead time. Nuclear explosion, no, much less. And so we applied a probabilistic model to assess the benefits of each. And next. Okay, so this is a representation of the 3 proposed mitigation of the asteroid impact. The gravity attractor, the question being what mass and what distance. We looked at 10 tons. The kinetic impactor, again, what's the speed and the mass, and the standoff nuclear explosion, what's the TAT equivalent, and at what distance. Next. So these are the effects of the asteroid risk on the probability of cataclysmic hit and the effect of global risk mitigation deflection. And you can see no mitigation gives you a very high probability distribution, non-nuclear activity tractors much less, and the nuclear option is the most effective. Now, as Seth properly said, there are all kinds of problems with that. We are not going to discuss here. It could be done perhaps at the national level for the people who are at the head of the strategic command. Next. Okay, so as we compare the effectiveness of the risk mitigation options for the whole Earth, you see the CCDF, the complementary cumulative distribution functions of primary effect fatalities for 100 years under various populations. First, no mitigation, then a gravity tractor, then the kinetic impactor and the non-nuclear, and we look both at those that we know, the asteroids that we know and the asteroids that we know exist, but we have not observed. And so this gives you a cumulative distribution function of the primary effects, which is the number of deaths, number of people affected. Okay, and the probability of exceeding them. So the asteroid impact risk and mitigations, and we looked here at the probabilities of death. Excuse me, I'm going to stop that. No, I cannot. Okay, the asteroid impact and risk mitigation and the probabilities of death. The probability that at least one person is killed by an asteroid impact in 100 years, 310 to the minus 4. The probability that 1 million or more are killed, 310 to the minus 6. But there are, of course, enormous uncertainties. And hopefully, improved observation will help us address these uncertainties with the longer lead time and improved deflection and trajectory. Okay, next. So this is the probability distribution. Again, the complementary cumulative distribution function, the probability of exceeding different numbers of deaths in this case. And you see on this one, the 310 to the minus 6 for 1 million people. Next. In summary, we have improved the existing probabilistic risk analysis models by aggregating what is known asteroids that we can observe and those that we believe out there. So what we have assessed was the risk posed by asteroid impact, the trade-offs involved in assessing the mitigation options, and if we choose to, the comparison with other threats. So civil defense appears to be the most effective countermeasure at this point. We don't have much else. So let me conclude next. In conclusion, the loss distribution of a long tail and a non-negligible probability of a large-scale cataclysmic event, as Seth pointed out earlier. The averages are not sufficient to provide the information. One must understand the full distribution to get at the extreme values. And the mitigation options are likely to be effective, assuming that we can see the asteroid coming. So the observation of asteroids remains a key priority, and improvements of observation will help reduce the risk, provided that the information that we receive permits response, and also remembering that observations and signals have false positive and false negative. And as was pointed out earlier, the false positive can be also very destructive. So these will be extremely effective in deflecting the asteroid and protecting the people on the ground. And I'm going to give you next reference to our work. You can find the papers that we have written on this in the proceedings of PSAM 12 and in the journal Risk Analysis in 2016. And that's the end of my presentation.
Thank you, Dr. Pate-Cornell, for very intriguing presentation. And I must say, I really enjoyed the paper in 2016 in risk analysis. And one point I drew from it, from your paper, Reinhardt et al., your paper, was the importance of the angle of incidence, which seemed to have been not as well studied in the past before your paper. So the angle of incidence affecting how much material is ejected into the atmosphere or the consequences for the climate. Okay, terrific. Thank you both for your excellent presentations. We now have about 25, a little bit more than that, minutes for discussion and question and answer. And in a moment, I'm going to invite people who are attending to pose their own questions. I know we have received at least 2 questions in advance before the session began today. One from William Kinsella at NC State University, and one from Ashton Mark at Duke Kunshan University. And so I might, in a moment, call on them to pose their questions orally. And then for other people, if you'd like to use in the participants list, you can use the raise hand function. And if that works, we will be able to call on you to pose your question orally. But before that, I have many questions, but let me pose a question to each of you, really about your a feature of the other presentation. So let me start with Elizabeth Pate-Cornell. I wonder what your reactions are to Seth Baum's point that even smaller objects, smaller NEOs or asteroids that may have a smaller physical impact on the Earth, but if they happened to land or their trajectory crossed near a national security sensitive location, they might trigger a human response of thinking that it was a nuclear attack or otherwise. Should we be taking these smaller asteroids more seriously in our estimates of the risk? And how would we incorporate that into the kinds of probability distribution or the cumulative distribution of risk? That's my question to you, and then I'll follow with a question for Seth Baum.
Yeah, that was a very good point, Seth. The thing is that the system by which that sort of thing is assessed by the strategic command, let's say in the United States, that's all I can talk about, is a relatively sophisticated one, totally classified, no need to say. And so one hopes that it's capable of recognizing that it's an asteroid. There has been all kinds of other phenomena that that could have caused this kind of stuff, but it's a very complex. It's a very complex systems of checking what's going on, and I trust that the probability that something like an asteroid goes through it is extremely small. But you're exactly right; it cannot be ignored.
And as you say, it's complex in part because it depends on the procedures and psychology and decision.
The procedures, yes, you're right.
Right, and the checks on decision making,
right,
by those government officials. Okay, so Seth Baum, let me ask you, following essentially on the same issue, are there elements of the kind of model that that Dr. Elizabeth Pate-Cornell and her colleagues were developing that might be helpful to the military or national security officials in distinguishing an incoming asteroid from an incoming nuclear attack. For example, maybe, I don't know if this is the right variable, but the angle of incidence might be different for a ballistic trajectory of a nuclear weapon or a guided cruise missile versus an asteroid. Is that right? Or are there ways that you think that this risk of false alarm war could be reduced by paying attention to some of these distinguishing features, or is that really difficult?
Yeah, so it is a good question. First, to briefly comment on your question to Dr. Pate-Cornell, I think it is indeed the case that the United States has a relatively sophisticated early warning system for detecting incoming nuclear attacks and asteroids and so on, and would be relatively capable of making that distinction. So perhaps there is still some chance that a mistake could be made. It may actually be other countries that have less sophisticated early warning systems where the value of the astronomical community, the asteroid research community, providing input to help distinguish an asteroid from a nuclear attack, it may actually be of greater value for those countries. Now, to your question regarding the value of whether models such as this that take into account the full range of asteroid parameters could be of value for making this sort of distinction, I think the answer is yes, definitely. So impact angle, I hadn't thought about that one before, but yeah, that does seem right, that we would in general expect if there's going to be a nuclear attack, it would probably come from a certain angle. And that if we see something that is coming from a very different angle, then that's something that we can use to help make a judgment on whether what we're seeing is a nuclear attack or something else. Other really important parameters are how large the explosion is going to be and how high in the altitude, with the altitude, how high in the sky will the explosion be, because asteroids, the collisions can be the explosions can be of a very wide range in tons and kilotons TNT, and can also be at a variety of altitudes. And the more information that we can get on that, the better we'll be able to distinguish one from another. But also, perhaps the most valuable would just be to have the basic information. Is this an asteroid collision in the first place, which can come from just monitoring the skies on an ongoing basis for incoming asteroids, especially in that smaller size range that produces explosions of the same yield as nuclear weapons. And if we can say, okay, there is an asteroid that's heading toward Earth, might hit at about this time, maybe even at this geographical location with this size of an explosion, and get that basic information out to the nuclear armed militaries of the world and their political leadership, then that could help them say, okay, we're expecting this. It's not an attack. The astronomers are pretty sure that this is an asteroid impact. Let's not panic. Let's not overreact to this. Even that basic information, I think, could be very helpful.
Yeah, of course, that raises the from a strategic game planner's point of view, the question of whether that could be gamed, whether the astronomer's reassurance could be falsified by a stealthy attacker, and then whether the defender would worry that that might be happening. But let me invite questions from our attendees. And William Kinsella, I don't know if you are, you posed a question in advance. We'd love to hear your question, and maybe Tim can help unmute you, or maybe you can unmute yourself. Um, yeah,
Okay,
Yes.
I got
Yeah.
the pop-up and I've unmuted. Can you hear me?
yes.
Yeah, so Jonathan, Seth, and Elizabeth, thank you all for doing this today. We're pondering the existential political crisis that we're living through, but when we think about asteroid impacts, it takes it up to a whole nother level. So maybe that's kind of refreshing in some ways. What I wanted to ask about was what I'm going to call epistemic gaps, or a question of agnotology. What is it that we do not know about near-Earth asteroids, both in terms of their physical characteristics, the number that exist, in terms of what the environmental consequences would be of an impact, in terms of human behavior? What are the things that we don't know about at all that we should know more about? This is the unknown unknowns question.
Okay, well, I will take this one.
Mhm.
Because it's an unknown unknown, all we can do is guess. And that is why we looked at this question of Fago, because it looked like it was probably something that would affect the amount of ejectile, the amount of stuff that could get out of ground. Apart from that, then I'm sorry, but I cannot really imagine another unknown unknown than that we have not looked into. Now I'm sure that Seth has an idea.
Yeah, well, I mean, there's something inherently difficult about describing unknown unknowns, because if we could describe them, maybe they wouldn't be unknown unknowns, maybe they would just be known unknowns. What I can say, and I spoke a bit about this in my presentation, is from my vantage point at least, the human consequences have a lot more known unknowns, at least in terms of the overall risk from an asteroid collision. There certainly still is uncertainty in the physical astronomical side of it, but it seems like we have an overall fairly good understanding of it. It's getting better all the time as we have better astronomy, as we have better analyses, such as from Dr. Patek Cornell's group. But to try to answer questions like, given a collision from a very large asteroid, how would human civilization handle it? We kind of just don't know. Or we know that it would be a major challenge for us, but would it be a challenge that we would endure with some difficulty, but otherwise pull through? Or would it really, collapse our civilization and cause the death of a very large portion of the species and so on? This is a question that I've tried studying, not just for asteroid collisions, but for a range of global catastrophe scenarios, and I find it incredibly difficult to answer. Now, there also hasn't been much work on it. Perhaps there should be more effort to try clarifying this, but it's perhaps also just an inherently difficult question to answer. Certainly not one where we can run some experiments, throw some global catastrophes out there and see how well human civilization handles it. We're just going to have to do our best to try figuring this one out in advance.
Okay, we also had a question submitted in advance by Dr. Ashton Merck. Ashton, are you there? And maybe Tim can help you unmute.
I am there, yes. Hi. Frankly, I'm not sure if I remember exactly what I asked in the forum, but and I think both of you kind of addressed what I was interested in, which was the relationship of the risks of catastrophic risks from asteroids and our preparedness for nuclear war during the Cold War. And so, I think both of you kind of spoke to those connections. So what I was interested in is, are we less prepared now for catastrophic risks from things like asteroids or nuclear attacks than we might have been during the Cold War, during the peak years of civil defense? This is a bit of a speculative question, given what you presented on. So that was what I was interested in. So you can talk about that a little bit. That would be great.
Well, let me take this one. I think I believe that we are a bit more prepared in a sense that we do not have to handle radiations. Handling radiations on human beings is very difficult. What we have to handle, though, is the uncertainties about human behavior. And I think that Seth has an excellent point. The most difficult thing to handle in these models is how are humans going to react. And it could be that they knew better how to react during the Cold War to a nuclear attack because it had been discussed more than that. Then we know now how to react to something like a large asteroid impact. So I would say altogether, we're probably less well prepared in that respect.
That's a great question. I'm probably going to be thinking about this one for a while, even after this event is over. Are we better prepared now versus then? It may well be the case that in policy terms, in terms of the active programs for preparing, what we had before would be better, despite the limitations in the civil defense programs that we had. It was just more of an emphasis, more of a priority than it was now. But that's not the only factor. Our science and technology is a lot better now than it was back then. That creates a whole range of options that we just didn't have before. And we are now using social media to identify the locations of survivors for natural catastrophes. That just wasn't an option in the 60s. We didn't have anything along those lines. We also have a larger global population now than we did then, which means if we're talking about these really extreme events in which the survival of the species may be in question, perhaps having more of us would be advantageous now. Alternatively, perhaps we're in a worse position now because we have a much more urban population now than we did before. There are fewer of us around the world who know how to sustain ourselves in the absence of civilization that feeds us and provides our basic needs for us. I certainly know, despite working on this, I wouldn't know what to do if I didn't have civilization to take care of me. I'd be in a tough spot, and the same holds for a lot of other people. I think more people now worldwide, a lot more people now worldwide than in decades past. So does this all add up to us being better off or worse off now than before? I don't have a clear answer to give to you, but it's a fantastic question and points to a number of potential policy activities and programs that we as a civilization could pursue if we wanted to increase our resilience to these types of events.
Those are two great answers. That's kind of what I was thinking. It's a trade-off of like, there's not the same kind of mass education that happened in the 50s and 60s, but then it's based on your presentations, the technology and the capacity to measure these things with great deal of precision seems to be orders of magnitude better. So thank you.
Yeah, very interesting question. And it makes me think of a couple of other features. One is we do have much more widespread and rapid communication technology now than we did even 20 years ago. And that could be helpful in spreading an alarm and improving civil defense. On the other hand, as we know, it can also spread false alarms. And actually the Hawaii incident was a small example of that, but there could be much broader false alarms. The other topic that this makes me think about, which goes beyond our focus on asteroids today, is whether we overstate the end of the Cold War. That is, to what extent are we still involved, perhaps in other forms of conflict, in great power conflicts, not as close to nuclear war, but asymmetric conflicts, and we're have been discussing that a lot with respect to interference in elections. and misinformation and other possible strategies. Okay, there are a couple of other hands up. I see Arden Rowell and then a Q&A post by Chase Hamilton. So Arden Rowell, great to see you. Please pose your question.
Yeah, hi everybody. Thanks so much, Seth and Elizabeth and Jonathan. So a couple of questions. I think the first one for Seth, and then the second one more for Elizabeth. So Seth, I really love this idea that asteroids are a counterexample to the normal GCR narrative. But why are you convinced, if you are, that we should think of them as a counterexample rather than as a reason to revisit how we define GCRs or what we think of as critical to making a risk a GCR? I mean, maybe frequency, for example, should just not be part of the definition of a GCR. Maybe we should only be looking at severity. So why think of it as a counterexample instead of as a reason to revisit definitions? And then I think this is mostly for you, Elizabeth. But clearly, I mean, as you know, with any kind of risk management, we've got options where we can focus either on basically mitigation or on adaptation. And of course, a massive quantity has been written on this in the climate change context. But your talk just made me think about how much some of that analysis may also apply when it comes to managing asteroid risk. And so I guess I'd just be interested in your thoughts on what strategies we might learn from on choosing between or looking at interactions between adaptation and mitigation. And I guess just one thought on that is maybe this can help us in thinking about which institutions are best situated for managing asteroid risk. I mean, it might be that as with climate change, that when it comes to the kind of adaptive strategies of changing civil infrastructure, et cetera, and we should expect local and domestic authorities to do well, and then it's only really going to be the mitigation type strategies, shooting them out of space, et cetera, where we're going to need something more like an international agreement. So thanks again. Such a fun and interesting topic.
So let me start with, Seth, you wanted to take that question?
Sure. I can comment on. So the question regarding the asteroid as a counterexample, and should we even have frequency in a definition of global catastrophic risk? So asteroids are one class of risk in which the frequency makes more sense to talk about because the rate at which asteroids of various sizes collide with the Earth is relatively well characterized. It's perhaps harder to draw out the same sort of distribution for other global catastrophic risks, nuclear war, for example. What's the frequency of nuclear wars? Very hard to say. I do agree with the basic point, and may not have been clear about this in my remarks, the basic point that global catastrophic risk should be defined in terms of severity and not in terms of frequency. And in other spaces, I've used a severity-only definition, which is to say that we should think of a global catastrophic risk as being risks of this very extreme high severity, regardless of what frequency they may have. Of course, if there is a risk that is high frequency and globally catastrophic severity, then of course that's exceptionally important as a risk. And if it remains the case that those risks are not getting attention, then yes, we definitely should be sounding the alarms on that, and perhaps to some extent we are. And likewise, if there are risks that are low frequency and low severity that are getting lots of attention, then maybe those risks are not worth our attention so much. Perhaps we can all agree on that. And to the extent that this, so what does this mean for asteroids as a counterexample to the narrative that the low frequency, high severity may get less attention? If anything, I think it strengthens the point. So I can say at least among my colleagues studying global catastrophic risks across the range of risks, there's a general sense that asteroids are a relatively low frequency global catastrophic risk, that we are more likely to get a large pandemic or a large nuclear war or something to that effect than a large asteroid collision. It's just the large asteroids just hit so infrequently that we're probably going to get a nuclear war faster. Yet the large asteroids get policy attention. And so if it's the case that we're getting policy attention to the really low frequency global catastrophic risks, then that's even more remarkable, even more compelling of a counterexample, I would say.
I want to be sure Elizabeth gets to respond. And then we also have a question from Chase Hamilton, which I hope we can squeeze in. And just to say that in my paper, which Seth, you kindly cited in your talk, I was also suggesting that over time, attention might shift more toward those extreme risks as we do better at solving the more routine risks, but it's hard to predict. Okay, Elizabeth Pate-Cornell, please go ahead.
Yes, and the word frequency assumes that we have seen things before. That's why I prefer to use probability than frequencies. And the probabilities that we use are derived indeed from statistics, but many other things. We cannot really talk about the frequency of nuclear war. We have to look at the mechanisms by which crises could deteriorate into nuclear war. And we do the best with what we have, but it's much more information than just frequency. That's for that part of the problem. The other one, of course, is the consequences. And for that, we have to get to a detailed analysis of where things can happen, and they have not happened before in large cities, for example, to be able to come up with a relatively good description of what we know and what we don't, which is the most important part of the story. Back to you.
Okay, great. And I think our last question comes from Chase Hamilton. If Tim, you could help Chase unmute. Thank you.
Can you hear me now? Okay, great. Thank you, Jonathan, and thank you, Elizabeth and Seth. I see that we're running low on time, so I'll make this quick. This question is somewhat inspired by the earlier question about comparing the asteroid risk of today versus the asteroid risk of the Cold War, but instead comparing the asteroid risk of today versus the asteroid risk of a pre-technological or at least a pre-nuclear era. Do you think that the risk of global catastrophe by asteroid is higher or lower now that we have nuclear weapons and other high capacity technologies?
Well, if I may, we can hope it's lower, but that will need to be demonstrated by the effectiveness of the means that we have that have improved. No question about that. Seth, to you.
I agree with that. Lower. The only way I could imagine it being higher is if civilization is now less resilient to an asteroid collision because we're so much more urbanized and so on. But my immediate reaction is that the biggest effect is now we have a much better chance of being able to deflect the asteroid away from Earth in the first place.
Thank you.
And presumably our deflection technology will improve over time. And Elizabeth mentioned several deflection strategies besides nuclear weapons, including the gravity pulling. And I've also read about changing the albedo of the object of the asteroid by painting it a darker or lighter color so that it speed but maybe we'll invent newer deflection methods. Any thought on that?
Well, I looked at the albedo stuff and I thought it was a very weak way of doing it.
Okay.
And so that the mass, in fact, the gravity tractor is more effective. So let's go with the gravity tractor, if we are going that way. And then there are other ways of doing it. Problem is, of course, once we have broken something, where are the pieces going? Which is another story that requires a lot of study from the physicist.
Yes, another kind of risk-risk trade-off. We might try to deflect the asteroid, but break it into pieces and then increase the probability that a smaller piece would still hit the Earth or cause harm. or be mistaken for an attack. So this has been a terrific and such an intriguing conversation. I'm so grateful to both of you, Dr. Seth Baum and Dr. Elizabeth Pate-Cornell, and thank you all to the attendees for joining us. We plan to have more of these webinars on planetary risk and other research projects and activities, and eventually in-person workshops again. So thank you both very much for joining us. Thanks, everyone. Look forward to seeing you again soon.
And thank you, John, to you for organizing this.
Our
Yes,
pleasure.
definitely. Thank you.